All right, we are looking at position, velocity, and acceleration. We've got the problem here. A rock is dropped from Free Bridge that measures 300 feet above the Arkansas River, and we're given the position function. So here's the model here that we're going to use, and we want to determine the position and velocity functions. How long did it take for the rock to hit the water? And what was the rock's velocity on impact? So that's kind of amazing. We can get both these guys right here just out of this little bit of information that we're given. We're 300 feet above the water, even though we are given quite a bit going on right here. So if you can imagine, you're standing up on Free Bridge, and if you can figure out where that's at, good luck on that. Uh, and the rock just kind of slides out of your hand and heads towards the water. So you don't give it any initial force, either up or down. It just slides out and falls towards the water. And somehow you were able to measure 300 feet. This distance from the rock to the water is 300 feet. So our initial velocity here is going to end up being 0. The initial velocity will be 0. Okay? And S of naught is going to end up being the initial distance that we are from the water, from the rock to the water. This is S of naught, represents initial distance. And so we can write our position function, and that is S of t is equal to negative 16t squared plus 300. Don't worry about where this comes from right now. Okay, that's something later on in calculus that we'll be talking about this. But and so you're just basically just plugging some numbers directly in right here. So there is our position. This is the model that's going to give us the relationship between the distance at time t, and that's be the distance from the rock to the water. What about the velocity function? If we take the derivative s prime of t, we call this v of t. This is known as the velocity, and if you take the derivative of this, you get negative 32t. Now, if the rock hits the water, how high is the rock from the water? Well, it's 0, right? 0. The distance is 0. And so if we let the distance be 0 and then we just solve for t in this problem, we can figure out how long that it will take the rock to hit the water. So in this equation right here, we're just going to solve for t, as you can see, square root both sides, and of course this is the exact value here. Of course we're just going to go ahead and approximate it at 2 decimal places. I think 2 decimal places is good enough, and so it takes about 4.33 seconds. Now what about how fast does the rock, when the rock hits the water, how fast was it traveling? Well, you take the derivative, that's this model here, and it's going to give us that. So you take that 4.33, or actually I'm going to take the exact value and plug it directly in, so we don't have any round off errors or anything. And we get negative 80 square roots of 3, but you know, what in the world is that really? Now, I didn't add the units on the end of this, but you understand that we'll have some units here at the end. So you plug this in. Of course, I went ahead and rounded it to 2 decimal places. So when it hit the ground, it was traveling at 138.56 feet per second. Now, of course, you notice this is a negative right here. And the negative actually tells us the direction that the rock was traveling, and this means it's traveling down. If this number is positive, that means it's going up. So that's the difference between velocity and actually speed. If we were saying, well, what was the speed of the rock when it hit the water, we would actually leave this negative off, and we would just say 138.56 feet per second. So the difference between speed and velocity there. And that answers our questions. So let's move on to the next problem.